Morning, good afternoon, and evening to everyone who is joining us today. I have a passion for data pipelines and analytics, and I am excited to get to speak to you all about it today. I'm the founder and CEO of Etleap, where we're building software that helps reduce the engineering burden and time to value for data pipelines. It's an ETL as a service solution that lets you integrate data from a wide variety of data sources and build data warehouses on Redshift and data lakes with S3 and Glue. And I'll tell you a little bit more about our service here at the end. This is a short talk, and we figured we'd rather go deep on a small number of topics that we see a lot in order to hopefully make it useful to you, as opposed to trying to cover the gamut of data lake issues at a surface level. An alternative name that we considered for this talk was avoiding the swamp, and that's really what I'm going to talk about. What do I mean by a data swamp? Well, lots of data is getting into the lake, but analysis aren't getting out. This could be the result of having a small number of data analysts with the requisite know-how to effectively use the data in the lake. So how do we go about bridging the gap to democratizing the data in the lake? Let's dive right in. There are lots of different names for the zones of a data lake, and different deployments have different numbers of distinct zones. But what's common to most data lakes is that they have some version of the following two zones: a raw zone and a curated zone. And in between these two zones, there might be other zones, and there are processes that do things like cleaning, that means applying rules to transform values and force types, structuring, that is turning raw data into tables, columns, and rows, file compaction, meaning consolidating smaller files into bigger ones, semantic partitioning, that's using attributes in the data to put different rows in different folders so that queries run faster, semantic consolidation, which means maintaining snapshots and historical views based on inserts, updates, and deletes, format conversion, quality control, etc. The list goes on. And one typical problem is that these are all potential barriers to data exploration. For many teams, it's only engineers that can create and operate pipelines in order to do these things. And so for analysts to do any sort of explorations, data engineers need to be involved. One of the key concepts that distinguishes a data lake from a data warehouse is schema on read. And this is a promise of flexibility. And it's great to be able to store raw data without concern for which parts are going to be used for future analysis. But if you don't have any strategy at all for how you're going to use it, what's more likely to happen is that preparing data for analysis becomes a daunting project. And much of the analysis that could be valuable is just never done as a result. And this leads us to our first proposition: enable exploration by giving all data a minimal schema. Enforce that all data in the lake has a minimal schema, even if it's just a way for readers to map to the set of fields available. This greatly reduces the burden on readers for getting an initial look at the data, because now they can run a SQL query against it with tools like Presto, Athena, or Redshift Spectrum. And this greatly increases the audience that can be given access to the raw data. In order to achieve a minimal schema to enable exploration, you might have to do a small amount of data processing. And that processing should not focus on performance and data semantics, because they're not a priority at this point. And it should not reduce the amount of information stored. In other words, you wouldn't do most of the things listed under the mountain here. Do just enough to make it possible to create an external table in your favorite schema store that maps to the data. Here's a way of thinking about it to help justify the added cost of setting up and maintaining this process. Data is read many more times than it's written. And so this initial processing cost is amortized over the future times that the data is read. Okay, so if you follow the principle that all data has a minimal schema, congratulations, you have made data exploration achievable for anyone who can write a SQL query. And that was a really good first step, but there is a lot more work that needs to be done in order to refine it to operationalize analyses. There are different methodologies that teams follow here, and this is where the different zones of the lake come in. A common pattern is that taking data from one zone to the next requires engineering effort in each instance to do these kinds of things. And in a lot of data lake projects, the data engineers are really busy and have a long backlog of work that they need to do. Another observation is that there's often some level of business logic encoded in these zone transition processes, and analysts often have a better handle on those processes, or what they should be, than the engineers do. As a result, there's back and forth between analysts and engineers, which leads to long time to value and wasted effort on both sides. And the end result of this is not just that some analyses take longer, it affects the way that analysts work and can significantly reduce the impact that analytics has on the business. So that takes us to proposition number 2. Strive to reduce or eliminate engineering and data curation. Now, this stuff isn't easy, and chances are that your specific data lake setup and requirements means that you have your own specific zones and processes to build out to get the data there. But in order to make your data lake initiative scalable, both in terms of bringing on new data sources and also more analysts, you want to reduce the amount of engineering work required with each new source or with each new analytics project. Here are some of the processes that can be standardized across heterogeneous data sources. First, we have event stream compaction. Is an example. So on the producer side of your lake, you might you want to keep batch windows small so that you have up-to-date data in your curated zones. But you don't want to end up with tons of small files in your lake, so a compaction process is necessary. But there's no need to write one for every event stream. Snapshot generation, this is a similar issue to the first one I mentioned. This one is on the curated zone of the lake. As more and more data gets loaded into the lake for a certain data set, it gets slower and slower to query for a point-in-time snapshot. So it makes more sense to have a standardized process for generating these so that high-performance querying becomes a feature of your lake as well. You want to know that your pipelines are delivering data on time and according to your SLAs. And while parameters for that might be dataset specific, the method for doing monitoring is typically not. And finally, as data is flowing through the zones of your lake, you want to ensure that it meets the quality standards that you define. Again, the specific quality checks that you run are probably going to be different for different data sets, but the way you run quality control can be generalized. For example, if you set up a framework like Great Expectations and integrate that with your lake, then you can have your data analysts write the rules at a data set level. In the ideal state, these are all pluggable so that when there's a new data source or a new analytics project, there's only configuration to do, and analysts can quickly unleash their curiosity and get to their interesting analysis without relying on engineers at all. Excuse me. But even if you don't ever get all the way there, it can be useful to think of these kinds of reusable components as features of your data lake that your data engineering team develops. And this way, the engineering team is focusing their efforts on enabling analysts instead of individual analytics projects. And this helps make sure that a lake can expand without becoming a swamp. Okay, so now you've enabled exploration of all data and you've successfully bridged the gap between the raw and the curated zone of your data lake. What's left? Well, for one thing, there is making the query snappy for interactive analysis and dashboards. And here's one pattern that we're seeing more and more: using the data lake as a source for materializations served out of a data warehouse. So here's our third proposition: make materialized view creation self-serve for analysts. Some people will probably argue that data engineers should be involved in each of the other steps in the data lake processes, but this is one where there are almost no reasons why they should be. Also, the good news is that if you're using Glue and S3 to build your data lake and Redshift as your warehouse, then Redshift Spectrum is a great tool for bridging the gap between data in your lake and tables in your data warehouse. You may also have seen AWS's announcement of Glue Elastic Views this week, which is another tool that can be used for this purpose. And one major advantage of doing this successfully is that you can avoid having two separate ETL processes for bringing data into your lake and into your warehouse. So with that, let me turn it over to Jobin, who will give you a couple of ideas on how to unify data warehouses and data lakes effectively.
Thank you, Christian. Good morning, everyone. As Christian mentioned, today I will be walking you through a few benefits and features of unifying your data warehouse and data lake, which of course is proposition number 4. Before we jump into details, let me give you an introduction of Amazon Redshift, as well as S3 data lake and what we call lakehouse architecture by combining both. Amazon Redshift is a fast, fully managed cloud data warehouse that makes it simple and cost-effective to analyze your data using standard SQL and leverage your existing business intelligence tools for analysis. It allows you to run complex analytical queries against terabytes and petabytes of structured data using sophisticated query optimization, columnar storage, and massively parallel execution. Now let's talk about Amazon S3. Amazon S3 is the most popular data lake, and it is chosen by customers because it has unmatched durability, availability, and scalability. The native features of S3 are exactly what you need from a data lake. Replication across multiple availability zones for high availability and durability, massively parallel and scalable. Storage scales independent of compute, and lowest storage cost at around less than 2.5 cents per gig. Amazon Redshift enables customers to directly query and join the data across both their Redshift and S3 data lake, giving the customers a lakehouse approach to the data warehousing. Amazon Redshift is the only data warehouse that extends your queries to your Amazon S3 data lake without having to move or transform the data. To load data into Redshift from S3, you can simply use Redshift copy command, and in order to export the data to your data lake, you can use Redshift unload commands in your SQL code and specify, say, Parquet format, and Redshift will automatically take care of the data formatting, partitioning, data movement in S3, etc. This ability to take the data from data lake into the data warehouse and back into the data lake is what we call the lakehouse architecture. This enables you to leverage the data in Redshift if needed to be available in the data lake, which will enable you to use other services like Amazon SageMaker or Athena to further process it for another, say, machine learning use case. Redshift Spectrum is a built-in feature of Amazon Redshift, which help you to query open file formats that you already use, such as Avro, CSV, JSON, ORC, Parquet, and more, directly in S3. This gives you the flexibility to store highly structured, frequently accessed data in Redshift, as well as keep exabytes of structured and unstructured data in S3 and query seamlessly across both to provide unique insights that you would not be able to obtain by querying independent data sets. Under the covers, we manage a fleet of thousands of Redshift Spectrum nodes, which are spread across multiple availability zones. These are transparently scaled and allocated to your queries based on the data that you need to process with no provisioning or commitments. And the key point to note here is that you will only be paying for the data you scanned using a particular query you fired. It is approximately $5 per terabyte of data you scanned. That would be the cost you will be incurring. Hence, as I mentioned, unifying your data warehouse and data lake opens up a lot of use cases and possibilities, providing you with much more flexibility when it comes to managing your data. Having that said, simply combining your data warehouse and data lake to design your lake house does not guarantee with optimal performance while running your queries. Let me talk about a few design principles or recommendations which will help you to organize your data lake in a better to suit your analytical needs. First, let me talk about partitioning your data. When you catalog your data, you create tables on top of the data in your data lake. Partitioning divides such table into parts and keep the related data together based on the column values such as dates, country, region, etc. The partitions act as virtual columns which are defined at the table creation, and they can help reduce the amount of data scanned per query, thereby improving the performance as well as reducing your cost. The next recommendation would be to use optimal file sizes. Queries run more efficiently when reading of the data can be done in parallel, and reading block of data can be done in sequential. Ensuring that your file formats are splittable will help with parallelism regardless of how large your files may be. However, if your files are too small, say less than 128 MB, the execution engine might be spending additional time with overhead of opening multiple S3 files, listing directories, getting object metadata, setting up the data transfer, reading file headers, etc., etc. On the other hand, if your file is not splittable or is too large, the query processing will have to wait until a single reader has completed reading of the entire file. That can reduce parallelism to an extent. Hence, the recommendation is to have the file size between 256 MB and 1 gig in size. Another recommendation is to use compaction. Compacting your data can speed up your queries significantly, and compacting data on a schedule basis to get your file size optimal is recommended. Say, for example, the daily compaction of files, which are under the hourly partition, if the hourly files are too small, is always recommended. Next, let's make sure the data ingestion is done in a proper way, such that if you need a staging location to store the raw files versus prep files for analysis, let's plan for that. Also, schedule it based on your use case, how often you need to execute those flows, and flows which are required to prep your data while executing. Now let us take a look at the next proposition, which is to use the right tool to interact with your data lake. And I'm going to introduce a few services. There are many services which are made available by AWS, but I'm just going to focus only on the popular ones. One of the most popular analytical service customers use to interact with S3 data lake is Amazon Athena. Amazon Athena is an interactive query service that makes it easy to analyze the data in Amazon S3 using standard SQL, standard ANSI SQL. Athena is serverless, and there is no infrastructure to manage, and you only pay for the queries that you run. Now, one of the questions that would come into your mind would be when to use Redshift Spectrum versus Athena. It purely depends upon your use case. For example, imagine that you need to join the data you have existing in your existing data in Redshift data warehouse with the data in S3 data lake. Spectrum would be the way to go. Say there is no existing data warehouse as of today, but the data resides completely in S3 data lake, and you have a use case to query the data. Athena would be the ideal option. And there are many other deciding factors as well. Using Athena, you can quickly query your data without having to set up and manage any servers or data warehouses. Simply point it to your data in S3, define a schema, and start querying using standard SQL. The most of the results are delivered within seconds, and with Athena, there may not be a need of preparing your data before analysis. This makes it easy for anyone with SQL skills to quickly analyze the large scale data sets. Again, with Amazon Athena, you only pay for the queries that you run, and you are charged $5 per terabyte of data you scan based on your queries. If you can also save from 30 to 90% on your per query cost to get better performance by utilizing compression, partitioning the data, and converting your data into columnar formats. Athena queries data directly in Amazon S3, and there is no additional storage charges beyond the original S3 cost. And it provides ANSI SQL interface, JDBC, ODBC drivers, and can handle multiple file formats and compression types. Again, it is easy to handle, which means it is serverless, of course, zero infrastructure to manage, and zero administration to do, and hence a very good candidate to explore your data lake really fast. Now let me talk about AWS Glue, another popular AWS service. For the data lake to be usable, it needs to have a defined mechanism to catalog and index your data. AWS Glue automatically crawls the data lake and constructs a single view across all the data sets to make it easy for the end users to discover the relevant data to use for their analytical needs. And it provides oversight on the quality of the data as well. AWS Glue is a fully managed service that provides the data catalog to make the data discoverable, ability to prepare the data for analysis, streaming, ETL, and much more. AWS Glue is integrated across a wide range of AWS services, meaning less hassle when you onboard your data lake or you're just getting started with building a data lake. Again, AWS Glue is serverless. There is no infrastructure to provision or manage. AWS Glue handle provisioning, configuration, and scaling of the resources you require automatically, and you only pay for the resources you used while your jobs are running. AWS Glue crawls your data sources, identify the data formats, and suggest schemas and transformations, and it automatically generates the code to execute your transformation and loading process. There is a lot more to talk about data lakes on AWS, but in respect of time, I'm going to have to stop here. With this, I will hand it over back to Christian to summarize the propositions we discussed and to give an overview of Etleap. Christian, please take over.
Thanks very much for that, Jobin. So in summary, these are the ideas we've shared with you for avoiding the swamp and making your data lake more useful. By giving all data a schema with minimal pre-processing, you enable analysts to access more data, and you also let them be part of the curation process from the start. By standardizing curation processes and thinking of them as features of your data lake, you decrease engineering effort and improve the quality of new data pipelines. By enabling data analysts to create their own materialized views, you make them more self-sufficient. By unifying your data lake and warehouse, you avoid having two separate ETL processes and enable analyses that use data from both the lake and the warehouse. And finally, by using tools provided by AWS, such as Athena and Glue, you can get more out of your data lake investment. Hopefully you find some of these ideas actionable if you've already built out your own ETL infrastructure. In case you're currently building out your ETL infrastructure or you're looking to augment what you already have, I'd like to tell you about the service that we offer here at Etleap. Etleap lets AWS customers stand up data warehouses and lakes in days or weeks, as opposed to months or years, and minimize or eliminate engineering projects. So what typically takes 6 months and 7-figure budgets with a traditional ETL tool can be done with Etleap in days or weeks and at a fraction of the cost. Here is a product overview. Etleap is a SaaS solution. It runs on AWS, and it integrates with databases, file stores, event streams, and applications of all kinds on the source side. On the destination side, it works with Redshift warehouses and S3 and Glue data lakes. All of this is set up through Etleap's web UI, where connections, pipelines, and transformations are configured and monitored. We provide tight integrations with your on-prem and cloud data sources and existing AWS warehouse and lake infrastructure. And in addition to UI-driven configuration, pipelines and connections can be configured through our API as well. And there are event interfaces for pipeline operation. Etleap can run as a hosted solution where there is no infrastructure to set up, or it can run in your VPC where infrastructure is set up with CloudFormation or Terraform templates that we provide for you. Either way, you get automatically scaling infrastructure that handles any volume of data and tightly integrated operational support. And that's it. Thank you very much for joining us today. There is still time to ask questions for our Q&A session that will begin momentarily. You can sign up for a free trial of Etleap on our website at etleap.com. Etleap is also available on AWS Marketplace, and we have a quick start that gets you up and running quickly if you want to run Etleap in your VPC. We also have engineers on standby right now who you can talk to about your data lake projects and our service. So to do that, go to etleap.com and use the chat function in the bottom right-hand corner.